Okay, so based on this interval, I'm going to start by summarizing the information on this example. I'm going to start by summarizing the information that I have, and then I'll try to use that information in order to compute a confidence interval. Right, so I'll start by finding the sample size, n, which in this case is equal to 23, right? I have 23 babies from which data is collected, and so that means that my sample has a size of 23. Then I find that the mean circumference for those 23 babies is 40.6, which means that 40.6 is an average that is computed based on only the 23 babies, right? So that means that that's a sample average. So I have that X bar is equal to 40.6. Then the standard deviation that I find here is 1.6. So 1.6 is the standard deviation of the head circumferences that we found for the 23-month-old babies, right? So that means this is the sample. Sorry? Okay. So S is going to be equal to 1.6. And so we have that sample size is 23, the standard deviation is 1.6, and the mean is 40.6. Then we have a 98% confidence interval, which is what we're trying to evaluate. So that means that we are going to try to take from a distribution and chop from both sides enough so that in the middle there's going to be 98%, right? So we want to find the values that will separate the middle 98% from the extreme 1% at the top and 1% at the bottom. If you've understood so far, please raise your hand. All right. So in this case, we have a couple of things. The first thing is that we don't have a large sample, right? So n here is smaller than 30. So that means I can't use the formula for large samples. But I was given that the distribution of the data is normal. And so this is the first thing. The second thing is that the distribution is normal. Because of this, I know that I'll be able to use the formula for the confidence interval, which is X bar plus or minus T alpha over 2, because it's a confidence interval, so I'm chopping both from the top and from the bottom. And then times S divided by square root of n. Right? So this is the third formula that we talked about last class. At this point, okay, so I have X bar over here, I have that value, I have the value of S, I have the value of n, and the only thing that I'm missing is the value of T alpha over 2. Right? So that means that corresponds exactly to the value that I'm trying to find to separate here, T alpha over 2. So far, so good. Please raise your hand if you understand. Okay. So T alpha over 2 is what I'm trying to find, with the caveat that this has 22 degrees of freedom, right? So this is for degrees of freedom equal to 22. So that's the row in which I'm going to have to look for my information. So here we go. We're going to go look at the table of the T table, the table for the T distribution, which is this one over here. And if this is the table that I'm looking for, just give me a second here. I know that I'm trying to chop 2% in total, right? So I'm trying to look at so 2% from both sides. And can please somebody confirm that you can actually see what I have on the board? Somebody just say yes on the mic.
You're good.
Yeah.
Okay, thank you. So I want to chop 2% from the extremes, right? So from the two tails, I want to chop 2%, so that's 0.02, right? So that means this is the column that I'm looking for. And then I'm looking at 22 degrees of freedom because it's always n minus 1. So that means that in this column, I'm going to look at this value over here. Right, so the value that I'm going to have for that T alpha over 2 is going to be 2.508. So that means I now can go back to.
Wait, how did you get that, Miss?
Okay, so I think that's the part that. Right, so I went to 0.02 on 2 tails because I'm trying to chop 2% from both tails, right? So I'm trying to chop 1% from the top, 1% from the bottom.
Yeah.
So that's 0.02 from the 2 tails, and then 22 over here, because that corresponds to n minus 1, so the sample size minus 1, 23 minus 1.
Okay. Because what I was doing was just like looking at the percentage at the bottom
Mm-hmm.
and using the number right at the top of it for my z.
Okay, so that only works if you have a z distribution, which is not the case in here. Right, so in this case, we have a sample that is not larger than 30, so it's a small sample, and so that means that we have to use the other values over here.
Okay.
Yeah. So then the value that we're going to use for this example is 2.508. Yes, somebody else was talking?
What happens if it is a z distribution? I didn't understand what he said.
Okay, in a z distribution, I'll do it in the next example. I made sure to do both cases. Okay, so with the value of 2.508, I'm going to go back to the example here, and now I know that this is 2.508. Right? So that means that my confidence interval here is going to be given by, the confidence interval will be x bar, which is 40.6, plus or minus, so I'm going to start with minus 2.508 times the standard deviation, which is 1.6, divided by square root of n, so that's square root of 23. So that's the lower bound. And the upper bound is going to be 40.6, so same thing, but instead of minus, there's going to be a plus. So plus 2.508 times 1.6 divided by square root of 23. Kyle, your hand is still up. Is that because you have a question? All right. And if I evaluate these, I'm going to get, I already did this before, 39.76. So this is going to be between 39.76 and 41.43. Okay, so this is my 98% confidence interval. If you understand everything that I did until here, please raise your hand.
Sorry, can you just go over the part you highlighted and
this?
think there in the formula? Just
okay, so here what I'm trying to say is we have everything, like all the other pieces, x bar, s, and square root of n. We already have that from the information that is given in the problem. To find the T alpha over 2, we need to look at the table, right? So that's the value that is going to separate the extreme 2% from the middle 98%. So at that point, that's when we go to the table over here. We say we're trying to chop 2% from both tails, given that my number of degrees of freedom is 22, always one less than the sample size, right? Because of that, I'm going to look at the number 2.508, right? And so that's going to be the value that is going to split the middle 98% from the extreme 1%. So that's the value that is going to go in my formula. That's why I can use it now here and there. Like good?
Yep.
Okay. So this is the value here and the value there. Do I have any questions? Okay, everybody can lower their hands unless you have a question. All right. So what that means is that I am, yes, Chloe, there's a question.
Yeah, because well, you said we could resubmit it, but there's like only one question that I have to redo.
That's fine.
Can I just send just the one question?
Yeah, you can send just the one question. Just clarify that in your problem, that that is the only one question that you want to resubmit.
Okay, thank you.
Yeah. So over here, what's happening is that we are 98% confident that the true head circumference, the true mean head circumference, sorry, is between 39.76 centimeters and 41.43 centimeters, right? Now, that doesn't mean that we know this, that we are sure that the mean is going to be between these two values. There is this very slight chance that we ended up with a sample that was either full of babies that had small heads or full of babies that had big heads, and so the mean is not actually that close to the actual mean for the population, right? There's still a 2% chance that we're in one of those extreme cases, but it's very unlikely, and so we're pretty confident that the actual mean is going to be between these two values, right? If we wanted to be more confident that my mean is going to be in the interval that I compute, so if I wanted to increase the level of confidence, what I would have to do is to increase the size of the interval, because that way I'll include more values, and so I'll have a better chance of actually capturing the mean for the whole population. Does everybody understand that? If so, please raise your hand. Okay, so I have several hands that are not being raised. Is there a particular
sorry.
Okay.
I have a question.
Yeah.
I don't understand where the number 22 comes from.
The number 22 is always, where's my pen? Here, this number is always n minus 1. So 1 less than the sample size.
Okay, thank you.
Yeah.
Wait, sorry, what is that for? The n minus 1 is for?
That's to determine which row to look at in your t-table.
Oh, okay. In the t-table only, right? Not the
Yes,
z.
in the t-table only.
Why is it the t-table and not the z-table for this question?
Because the z-table is, okay, why is it the t-table in this question? Because n is equal to 23. This is smaller than 30. So this is not a large sample, and we can't assume that our distribution is going to be normal.
Okay.
Okay, so we can always assume that the distribution is going to be more or less normal if the sample size is larger than 30. But if the sample size is not larger than 30, then we're going to have to use the t-table.
Okay, thank you.
Okay, and because when the sample is not large, we have a little bit more variation with every new person that we include. Then the limits that we choose are going to depend on the sample size. That's why we have to include that as a factor of the distribution that we're looking at.
Okay.
I still have Alex, Phil, and Aaron with their hands up. Is there a question? There you go. One hand down. Phil, all right. Okay, so everybody can lower their hands unless you have a question.
So Miss, just to clarify.
Yeah.
So for when it's under 30, you do n minus 1, and then the percentages that's left on the side, you use that too to get 2.508.
Okay, so let me just go back to the table.
So
yeah, so you use the n minus 1 to look for which row you need to look for, right? So here that was 22.
Yeah,
that's our row.
0.2 left over.
And then you can either look at the percentages here at the bottom, which tells you the confidence level, but that's only going to work for confidence intervals. Or you can say, and this is the intuition that I would like you to get, because we're going to elaborate on this later today. You can say, okay, well, I'm trying to chop 2% from both tails, right? That's what we're trying to do. Does that make sense?
Yeah.
So we're trying to chop 2% from both tails, which means that that's the column that we are going to look for, right? It ends up being the same, but you're going to see we're going to have another type of example, in which case the part at the bottom over here is not going to be as useful. So that's why I like the idea of looking at this before.
Okay.
Yeah.
Miss, there's something I don't get.
Yes.
You say that we were trying to chop 2% from both sides, but if it's 98%, wouldn't it be 1% for each side?
Yes, we are trying to chop 2% from both sides together, right?
Oh,
so
okay.
additionally, from both sides, we're trying to chop 2%, which means that we're chopping 1% on each side.
Okay, thanks.
Yeah. Okay, I still have Caroline and Josh with their hands up. All right. So, and then I have a message in the chat. Okay, well, Alex, you're in luck because you have an extension for the class, for the assignment. So I'll elaborate on that in a second. I'm going to do a second example that involves the Z distribution, and then I'll give a couple of announcements that I want to give the class marks, a bunch of information that I'm sure you're going to be interested in.
Miss?
Yep.
You had sent an MIO for the extension on the research
Yeah.
part.
Yes, but I haven't sent an extension about the assignment, so I'll explain everything.
Okay, thanks.
Yeah. All right, so for the second example, you're going to have, suppose that out of 14,881 convicts who escaped from US prisons, only 7,067 were recaptured. We're going to have that P is the proportion of all escaped convicts who eventually will be recaptured. And we're going to find a 90% confidence interval for the proportion of all escaped convicts who will eventually be recaptured. Okay, so a lot of information, but here's the main idea behind that. So we have a population. We have a population which has a given proportion, right? So my population is the population of people that have, convicts that have escaped. And we're trying to determine P, which is the proportion that will be recaptured. Will be recaptured. Captured. Now, we can't really gather information from all of the people that escaped, but we can gather from all the people that will escape at any given time, but we can have information about the people that have already escaped and determine how many have been recaptured. Right? So that means this is our sample, and we can determine the proportion that were recaptured. So from my sample, which has a size of 14,881, I know that the proportion that were recaptured is 7,067 divided by 14,881. If you understand this, please raise your hand. Okay, so we have that. This is my sample proportion, and I'm trying to find an estimate for the actual proportion. But of course, I know that my actual proportion is probably not going to be exactly the same as my sample proportion, and so that's why I want a confidence interval. So just to get an estimate for this, we have, this is the same as 0.4749. So this is the estimate that I'm going to use, right? So approximately 47.49% of the convicts that escape from prisons are recaptured. Now, because this is a proportion, so this is a proportion, and I have that n times p hat is equal to 7,067, and n times 1 minus p hat. So here I'm just verifying the assumptions. Remember, we had a column that was assumptions, and I needed to make sure that my assumptions are verified. This one is going to be 14,881 minus 7p67. So this is 7,814. Both of these are larger than or equal to 5. And so I know that I can use the formula for a confidence interval, which is p hat plus or minus z alpha over 2 times square root of p hat times 1 minus p hat divided by n. If you understand everything that I've done so far, please raise your hand. Yes, what's up?
I don't understand what p hat is.
P hat is just my estimate for the proportion, right? So I have the proportion is this idea that I want to estimate, but the way that I'm going to estimate it is by actually computing the proportion for my sample. Okay, so the proportion for my sample is just the number of prisoners that were recaptured among all of the prisoners that escaped.
And what's the bigger or equal to 5?
This was in last time's lecture. I said, okay, remember there's always strings attached to the type of conclusions that you can draw. And depending on the case, the strings attached are going to be different, right? So for example, you either have to check that a sample is large if you're trying to if you're trying to find a confidence interval for the mean. If the sample is not large, then you need to make sure that the distribution is approximately normally distributed. And in this case, the condition that I need to use, that I need to verify in order for me to assume that this is actually going to work, is that n times the proportion is going to be larger than 5, and n times 1 minus the proportion is also going to be larger than 5. This is just a condition that you can verify, and as long as this is the case.
From the table, right? Like the
yes,
big table.
Yes, it should be the last row, the second column. Row.
But I don't understand what like the actual 5 is. Like,
okay, so this is just
not
really. So the idea over here is that basically you don't want the proportion to be too tiny or too large, because what that does is that then your distribution you would expect to be skewed, and you don't want a distribution that's skewed. Because essentially what we're doing here is we're doing an approximation through a normal distribution, and the normal distribution has to be symmetric, right? If your proportion is either too small or too large, and you have a distribution that is skewed, then the normal distribution is no longer a good approximation, and so this interval no longer applies.
Okay, thank you.
That's the idea, yeah. Okay, so we're going to use this formula over here. We already have. Same thing, I always do the inventory of what I already have so that I have a clue of what I'm going to replace. So I already have p hat, that's over here. And so I can replace that one and that one as well. And I already have the value of n. That one's over here, right? And so the only thing that I have left to find is, again, z alpha over 2. Okay, now there's a couple of ways of finding z alpha over 2. I want to go back to the table with the z distribution, because again, this is going to be important. We're going to use it a little bit more in the second part of the class today. So z alpha over, give me a second. Looking for something? Second drawer. Okay. So you have, if this is the distribution, z distribution, we want a 90% confidence interval, right? So that means we want 90% over here. That means we're going to try to chop 10% together from both sides. So that means I'm going to have to chop 5% from the top and 5% from the bottom, right? So I'll have 5% that I can get rid of here and 5% that I can get rid of here. Does everybody understand that? Please raise your hand if you do.
Do you mind repeating that, please?
Yes. So what I'm trying to find is the values that separate the middle 90% from the 10% that is too extreme, right? Because I want to determine what's a typical 90% in the middle and then what's extreme on the sides. So if I'm going to keep only 90% in the center of my distribution, then that means that I'm going to have to chop a 10% altogether from both the upper tail and the lower tail. If that's the case, then that means I'm going to chop 5% from the upper tail and 5% from the lower tail.
Okay, thank you.
All right, so then that means I'm going to chop 5% from here and 5% from there. But instead of looking at both the positive value and the negative value, I'm only going to look at the positive value. Remember? So we said I'm going to just look for this value, because I know that the other one is just negative, the corresponding negative. That means, yep.
How do you know that the 90% is in the middle and it's not like a little bit to the side? Or?
Okay, because this is a confidence interval. The idea here is that, that's a really good question. It's a question that is difficult to answer without getting into the technicalities. But the idea is that we want to get an interval that is the narrowest possible and that includes 90%. Okay. If I start shifting it a little bit to the left, so if I try to find maybe the 90% that is not exactly in the middle, but a little bit more like this, because this tail is not as tall, then my interval is going to become a little bit wider, right? To compensate for the percentage that you chopped here. So the percentage that you chop from this side, so like if my distribution is like this, let me just explain that. So if you start with a distribution that is like this, centered, and then you try to move your interval a little bit that way, you'll chop, let's say, I don't know, some percentage over here, but to compensate for that, you're gonna have to, like the difference over here is going to be larger. And so your confidence interval is going to be larger like this, right? Whereas what you want is the smallest possible confidence interval that will still contain 90% of the information.
Okay.
Right? So that's why we want it centered exactly at the middle.
Okay.
Does that make sense?
Miss?
Yeah.
I might have like checked out for a second, but I don't really understand what the 95%, 5% underneath is, or if that's what you just explained above.
Okay, so this I'm gonna get rid of, okay? This is just like a side explanation. But the 95% and 5% over here is because I know that I need to chop 5% from the bottom, 5% from the top, but I'm going to try to use my Z table. And so I'm only going to look at the 5% that I chopped from the top so that I can look for the 95% here in my table. Does that make sense?
Not really.
Okay,
if you're
so
looking for 90, why are you looking for 95 now?
Okay, because this 90 is assuming that I've already chopped the 5% at the bottom.
Oh.
Right, so this is the 90% plus this 5% that I haven't yet cut.
Okay.
Right, so this is like both of these, and then I find just this value. That's the value that I have over here. Okay? All right, everybody lower your hands. I have Victoria, Alex Fossey, Gianni, Blake, Raphael. Okay, now, does everyone understand this part? If you do understand, please raise your hand. Okay, so we're trying to find the value that separates the top 5% from the rest of the distribution, which means the rest of the like the other 95%. Okay, let me see. Okay, so I'm chopping 5% from the top and from the bottom, but I know that this is just going to be negative whatever value I find here. So that means I'm only going to look at the value that separates the top 5% from the rest, and then I'll know that the corresponding value is just going to be the negative. Okay, that's the idea here. So this is the value that I'm looking for. That's like the big question that I'm trying to answer over here. And so here we go. We're gonna go to the Z table, which is somewhere around here. Okay. Please, somebody let me know if you do see the table.
Yeah.
Yes.
Yeah, okay, good. So this is the table that you've had from before. And you know that if you want to look for the 95%, you're going to look inside the table at the value that corresponds the closest to 95%, and then we're going to look in the margins to the boundary that corresponds to that number. Okay, so that means 95% looks like both of these values, and it looks like it's exactly in between these two values. Does everybody agree with that? Can I see a show of hands for those of you who understand this? Okay, so that means that the value that I was looking for is 1.6 and some value between 0.04 and 0.05, which means that the value I'm looking for is going to be 1.645, which is between these two values. Is that okay?
Miss, why are you going between the two?
Because I'm looking for 0.95, and this is exactly in between 0.9495 and 0.9505. Right? If 0.95 were closer to either of these values, I'd just go with the one that it's closest to. But in this case, it's exactly in between those two values, and so I can't really choose between the two.
Okay.
All right, so that means the value I was looking for is 1.645, and now I'm good to go. I can actually plug into my formula for the confidence interval, and I'll be done with it. So I'll have that this is going to be my confidence interval, my 90% confidence interval is going to be p hat, so 0.4749 plus or minus 1.645 times square root of 0.4749 times 1 minus 0.4749, which is 0.5251, divided by n, which is 14,881. And if you evaluate this, you're going to find that the confidence interval that you'll find will be 0.4682 and 0.4816. Do I have any questions about this?
I have a question.
Yeah, what's up?
Did you have to look at the Z table to find your 1.645?
Okay, so the other option is, and some of you might have realized this, is that if you go to the confidence, to the T table over here, and you go to the confidence level, if you go to 90%, there's a line that tells you the Z value, right? And so that Z value that you find is also going to be the 1.645. I mean, you can do this if you want for the confidence intervals, and it will work. Whenever you try to find Z, you can look at that line, and depending on the confidence level, you're going to be able to find that.
Wait, where?
In the T table, you see there's this line over here that tells you the confidence level. Now we were looking for 90% confidence level, and the very last line tells you the boundary for the Z distribution. So here you would have found the 1.645.
Okay.
Okay. Now that's
so
fine.
Not 95.
For 95 it would be 1.96. But like
Okay,
here the
but
confidence level is the confidence level is 90, right? So it's 1.645. Right. Now that's going to work, but it only will work for confidence intervals. And that's why I want you to still be able to read the Z table in the other case, because when you don't have just like when you're not chopping from both sides, when you're chopping just from one side or from the other side, you're going to have to use your other table, right? So it is okay if you use it for confidence intervals, but keep in mind that the other table you should also be able to.
Is it above 30? Like
yes, for above 30. So like here, technically you could use it for like 40, 60, 80, and 100 and 1000 as well, but this will like, we'll generalize it and we'll say, okay, if n is larger than 30, then we can use it for Z right away.
Okay, thank you.
Yeah. Okay, any questions? Okay, so I'll go back to the main whiteboard, and I think I have.
Yeah, just one question here.
Mm-hmm.
It's when you have 1.645 on the bottom formula, right? Isn't it supposed to be divided by 2? The very bottom.
So the divided by 2 was the reason why we looked at 0.95 and not 0.90, right? So that divided by 2 just means that you're chopping half the percentage at the top and at the bottom.
Okay.
Okay. Yeah. All right. Questions, comments, anything?
I have a question.
Yeah. What's up?
I don't know why, but I just don't know where you got the 0.5251 from.
Oh, that's just 1 minus 0.47. So this is 1 minus 0.4749.
Okay.
Yeah. Okay. And so if we want to interpret this, all that this is saying is that I am 90% confident that the true proportion is between 46.82% and 48.16%. Okay, now, again, there's a chance that my parameter is still not in this interval, right? I only have a confidence level of 90%, which means that there's still a 10% chance that I found an interval that actually doesn't contain the true parameter. And I have no way of knowing because the only information that I have is the information that I got from my sample, right? So that just means, okay, well, if you want a better, like a better estimate, if you want a higher level of confidence, then you're just gonna have to make your interval wider to make sure that you have more values, and so that the probability that you captured your true proportion is going to be a little bit higher. Does that make sense for everyone?
Yeah. I have a question. Is it
Yeah.
okay if we just put the interval on instead of like putting the I am 90% confident that?
It's okay unless I ask you to interpret it.
Oh, okay.
Yeah. So this is these are the two examples that I wanted to cover about confidence intervals. And here are the announcements. This is just like a clip, like a news clip. So there you go, announcements. The first thing is that assignment 4 is now due. Assignment 4 will be due on Sunday at midnight. Okay, the idea for this is just that you have the time to correct based on what we did today. I rather like rework on what you have and do it properly than just like let it go and then never learn it. So due Sunday at midnight. The reason that I don't make it due on Tuesday is that I would like to have corrected it by Tuesday so that you have the feedback for that. The next thing is that it has been decided by the QM course committee that there will be no final this semester. No final exam for a course. This means, of course, that you will have no final exam, but it also means that the class mark is now going to become your grade for the rest of the semester. Where do I post the feedback? So the feedback that I'm posting, I'll do it individually for this case. So because you're submitting everything on Leia, it's possible for me to hand back all the assignments on Leia as well. Right, so this is the first assignment that you're handing in on Leia. I'm just like basically giving it back on Leia as well. There's a possibility for teachers to just hand in your assignments. Is that okay, Carolyn? Okay. So then no final exam for the course, which means that you're going to be evaluated only on assignments, tests, and the research project. Which brings me to a couple of things. The first thing is that I'm going to have 1 or 2 more assignments, but I want to discuss that with you because I want to see how you are on amount of work that you're doing at home. So I'm going to ask everyone to unmute your mics, and I would like to know if you're having a lot of homework. Okay, so we're going to start with today's lecture, which is about hypothesis testing. Hypothesis testing is a section that is counterintuitive and that you have to think quite a bit about. I'm putting that warning from the get-go so that you make sure that you ask me questions as soon as anything comes up. Okay, so it's really, really important to understand everything that I'm doing along the way. Because otherwise it's easy to lose track of what we're trying to do, okay? So here's the idea. In hypothesis testing, this is the way that we'll actually be able to draw conclusions from data. Before I start, I have Blake, Johanna, Alex, Raphael, Kyle, Jenny, Alex, Roshan, and Carolyn that still have their hands up. I assume that there's no questions just yet, so you can start by doing this. Okay, so what I'm going to start by saying is that one of the main reasons to do statistics is to inform us gain information, maybe let's say gain information about what happens in real life. Okay? So we collect some data and we are able to determine what happens in real life. Some examples of this could be to answer the following questions. The first question that I'm going to about here is, for example, we could determine whether it is whether a new drug, so is a new drug more effective than an older version of that same drug, right? So the older version. So maybe a treatment for a given disease has been found, and we would like to determine if the treatment is more effective than an alternative treatment that there is for that given ailment. Another question that we could ask is, okay, well, a lot of people are talking about climate change and whether the temperatures of the earth are actually changing, but we could ask if, you know, it just happened to be a hot year, a given year, or if we can actually say that there is a significant increase in the temperatures of Earth, right? So that means, has there been an increase in the temperature of Earth? Right? So that's a question that we can ask. So if I see some kind of difference, is this just a random? Is this just out of random chance, or is this or is there something actually there? Right? Is there an actual reason for me to observe that difference? Another question that we could ask is, for example, does pulling an all-nighter before an exam actually make you more likely or less likely to pass the exam? Does pulling an all-nighter for an exam make you more or less likely to pass an exam? And is it, does it make you more likely or less likely? Does it actually make a difference? And if so, does it make a good difference or does it make a bad difference? So these are questions that we could try to do, try to answer using statistics. But the idea is mainly to say, okay, well, all of these questions can be answered by looking at some data, right? We can start by collecting some data, and then we are going to observe something from the data. But once we have actually collected that data, once we have actually, gained that information from a given sample, is the information that I gathered enough to say yes or no to either of these questions, right? So do I have enough information to confirm or to refute some statement? Okay, so after gathering data, we'd like to determine if something is due just to chance or whether there's an actual reason behind observing a given result. After gathering data, we want to determine whether the value that we observe, what we observe, is due to chance or whether there is a reason, another reason behind it. Right? So that comes particularly as a question after what we saw last week, right? So last week we said, okay, even if we know what the average of a given population is, we know that if we take samples, we should expect some kind of variability from our samples. Now, the question over here is to say, okay, from this data, if I observe a given result, is that result a consequence of just the variability that I should expect between one sample and another, or is the result actually caused by something else? Okay, so for the first question, is a new drug more effective than the older version? What we can say is, if I observed an improvement, can the improvement be explained by chance alone? Right, so is it possible that the improvement that I observed was just, fluke, something that I could have observed just because of random chance? Maybe I was just as likely to observe a decrease in the efficacy of the drug. Another option is to say, okay, for the increase in temperatures of Earth, is it possible that I just happen to be in one of those hot years or hot decades that are bound to happen at some point, right? Is it possible that I'm just in one of those decades that just out of random chance ends up being hotter, or is it actually that different enough for me to conclude that there has been an increase in temperatures of Earth? So can increase in temperatures be explained by chance alone? And in the last case, so does pulling an all-nighter before an exam make you more or less likely to pass an exam? Well, we'll collect some data, we'll run an experiment, we'll have the students pull an all-nighter before the exam and have not pull an all-nighter before the exam. Well, okay, can the difference between these two be explained by chance alone, or is it that actually pulling an all-nighter makes a difference in what the results are going to be? So can the difference in scores be explained by chance alone? Okay, so you get the idea. What we're trying to determine is, if I observe something from the data, would chance be enough for me to explain the results, or is there something else that is at hand? Okay, so the general formulation is going to be, can something be explained by chance alone? This is the way that we're going to think about testing hypotheses and drawing conclusions from data. So the first option is, if chance is a reasonable explanation for what happened, then it might be that I don't have anything to worry about, right? So that means maybe if chance is a reasonable enough explanation for one drug doing better than another, then that means that this drug is probably not significantly better than the original drug that I had. Same thing, if the temperatures can be explained just by chance, then there might not actually be global warming, but it might just be a decade that happened to be a little bit too hot. Or if I see a difference in scores that is not too different, that can be explained just by chance, then it might just be, that I had a group and it had some kind of deviation from, there was some kind of difference between the two groups, but that was just out of random chance. I knew that there was going to be some kind of difference, and the difference is not large enough for me to conclude that pulling an all-nighter actually makes a difference, right? So if chance alone can explain, if chance alone can explain it, whatever it means, so either the temperatures or the improvement in the scores or the effect of the drugs, if chance alone can explain it, then there's nothing there. I don't have anything to worry about. There's nothing worth noting. If chance alone cannot explain it, again, whatever it may be, so depending on the context, what we're trying to explain is going to be different, then there might be something there. There might be something there, right? So if just random chance is not enough to explain the increase in temperatures, then maybe it's a reason for worry. Maybe it is reasonable to think that there's going to be global warming. If there is a pretty significant difference in the scores between people that pulled an all-nighter and people that did not pull an all-nighter, then it might be not because just random differences between the two groups, but actually because pulling an all-nighter makes a difference. Either it makes people better at the exam or worse at the exam, and so on. If you understand what I've explained so far, raise your hand. All right, so I have most people with their hands up. As I said before, if you have any questions, you're welcome to interrupt me. So what I'm going to do now is work through an example based on how we're going to draw these conclusions, and then hopefully I'll have the time to do 2 formal examples with the actual formulas that we're going to use for this section. So we have example. And in this example, I'm going to have the following scenario, which is that a math teacher claims that he has found a new teaching method that guarantees that his students do better than average in math. Okay, so there's a math teacher and he has found the magical elixir that makes students be better at math automatically. Okay, he has this new technique, it makes his students better. Now, of course, he's not silly, he's a math teacher, and so he knows that he's going to have to prove that his method is good. Otherwise, people are not going to believe him, right? And so he says, you know what? I'm going to show that my students are better. In the last ministerial exam, which was set to have an average of 72, so in an exam whose mean is known to usually be 72, his class got an average of 75. Right, so he was like, clearly, my class has done better. And then he gives himself a star. So I have my math teacher over here. He's going to, I don't know, there he is. Long arms, but okay. So he is pretty happy because his students got an average grade of 75. And so he says, okay, they're definitely better than the rest of the students. Does anybody have any concerns about why this might or might not be true? What questions would you ask him if we were to say this to you? What would you say? You think this is a reasonable enough argument, or do you think that there's some reason to doubt him? Anyone?
Miss?
Yep.
What is the drawing with
I'll explain.
Okay.
This is just the teacher. He says, my class got a 75. I'm just really happy. Okay. He's like, yay, my class did better than everyone. Well, because he's congratulating himself. His class did better.
Okay, I thought it was like a.
No, there's no significance to it.
Okay.
I'm just having fun with the stamps. Yes.
75 isn't that much of a difference, so it's probably just due to chance or that his students are naturally smarter.
Okay, so that might be an option, right? So then there's the possibility that we're like, okay, well, 75 doesn't look like it's that much bigger than 72. So like 75 is not that much bigger than 72, right? And in particular, we don't know if we should expect the results to be fairly close to 72 or if they vary a lot around 72. And so Caroline in the chat had a good idea, which is that we could say, okay, well, 75 is pretty nice and everything, but what was the standard deviation of the results, right? What was the standard deviation? We could ask, right? So standard deviation of the results, either S or sigma. How much did the results vary? If they varied a lot, then we should expect a lot of variation in the scores from one class to another. And so 75 might be a pretty, reasonable result to expect. Whereas if the results didn't vary a lot, then the average for the class should have been a lot closer to 72, and 75 actually is a result that is very impressive. Does everybody agree with that? If so, please raise your hand.
No, Miss, could you repeat that, please?
Okay, so I have to worry about the standard deviation because if my results were very variable, right? So if the students in this exam usually score, with an average of 72, but the scores range from 30 to 100, then, you know, it might be reasonable to expect that my class will have an average that might be a little bit off of 72, right? It might be quite a bit larger or quite a bit smaller than 72 because I should expect some variation in the results. Whereas if normally we have that the results are very, very close around 72, then I should expect all of the averages for all of the classes to be fairly close to 72, and so 75 might actually be really an impressive score. Does that make sense?
I think so, yeah.
Okay, so the idea is to determine whether 75 is an impressive score with respect to 72 or not. If the scores usually vary a lot, then 75 might just be due to chance, whereas if the scores vary very little, then that means that 75 is probably going to be a very extreme result.
That makes it much clearer. Thank you.
Okay. Okay, so standard deviation was a good idea. Then there's the possibility of looking at more things. There's a median, you know, what the results were, but in this case, we're only going to worry about mean and standard deviation, and there's one little bit of information that is also important, which is how large the sample was, right? How big is my class? If I got an average of 75, but I had 2 students, well, it's not that impressive, right? I have one student that was really strong and then the other one that was more or less strong, and that's it. I got an average of 75. Whereas if I got an average of 75 from, I don't know, 1,000 students, then that means that a lot more information gave me a result that was still higher than 72, right? So that means if I have a larger class, this difference, the fact of getting an average of 75 is a lot more significant. Does everybody understand that? Do you have any questions about that? All right, so 2 main things. First, if the standard deviation is, so the standard deviation tells me how much variation, standard deviation tells me how much variation to expect. And so if the standard deviation is large, then a score of 75 is not that impressive, right? So that means that large standard deviation means 75, the grade of 75 is not that impressive, right? And then we can look at the sample size, or the class size in this case, which tells me that this is kind of like saying the amount of information that we have, right? So if we have a very large class, then that means that 75 as a grade is a lot more impressive, because even though I have a lot of people, I know that when I have a lot of people, my average should get a little bit closer to the actual average of the population. That's what we saw last week, right? So more information means I should get a pretty good estimate of what's happening for my whole population. And so if I had a very large class, then my result should be fairly close to 72. And if it's not, then that means that there might actually be something there. Please raise your hand if you understand.
It's not to be annoying, but I was writing down and I didn't really understand that.
Okay, so what I'm saying is just that if the sample size is larger, we should expect the results to be a lot closer to the actual mean for the whole population. And so if I get a result that deviates from the mean for the whole population, then that's a lot more impressive, and it might not be caused just by chance, but rather by something else, right? So it might actually mean that his method is better. All right, so now that we know that we should be asking about the standard deviation and the sample size, he's like, okay, you know what? I don't want to kid anyone. I'm not trying to trick anyone. I just think my method is good. So let's look at the standard deviation and at the sample size for my class. So he goes and says, okay, actually, the average is usually 72, and the standard deviation is usually, for this test, is usually, what value did I give it? 10, 12? The standard deviation is, I will get this at some point, 12. And the class size that he has he actually has 30 students in his class. So from a sample of 30, he got an average of 75. Now, it's not clear whether this is good yet, right? Like, okay, so I have this extra information. Now, how do I deal with the extra information that I was given? So that's what our goal is going to be today, to try to actually be able to conclude and say yes or no based on what we have from a given sample. Okay, so let's think about the person that was asking all these questions. So we're asking questions to the teacher, and we're going to say, all right, I'm going to be willing to say that your method is better. So I'll be willing. We are willing to accept, maybe to believe, that the method is effective if the class scored better than 95% of all classes that are this large, of this size. And the idea behind this is to say, okay, well, it's very unlikely that just out of chance that you will just have happened to have one of the top 5% of the classes. There's only a 5% chance that you'll have one of those strong classes. And so if you do place in the top 5%, I'm going to accept your explanation that that's because your method is better. Okay, that's the idea. Okay, so willing to believe that the method is effective if the class scored better than 95% of all classes of this size. And here's the reason. It's unlikely that the class is in the top 5% just by chance, right? There's only a 5% chance that they're there just by chance, right? So it's unlikely that they're in the top 5% just by chance. So if the class did score in the top 5%, I'll believe that it is because the method works. Everybody lower your hand and raise your hand once you have finished writing. All right, okay, so let's try to reason this out. We are saying that we are going to believe that the class did actually better than average due to the method, as long as they placed in the top 5%, okay? First thing is that 5% is completely arbitrary. I could have said that threshold higher. I could have said, okay, I will only believe that the class did better because of the method if they're in the top 1%, or if they're in the top 0.0005%, okay? And that depends only on me and on how sure I want to be that I'm making the right decision, okay? In this case, it's just a teaching method, so I'm willing to believe it without having to be that demanding on the amount of evidence that I need. So here's what we learned last week. So what we had last week is that the average of a given sample followed a normal distribution if my sample was more or less large, and that normal distribution was centered at mu and had a standard deviation that was sigma over square root of n. Okay, I just want you to get this idea. Don't get hung up on the formulas. It's just to get an idea of where we should be. Okay, so here's the thing. I am going to assume, so the whole point over here is that I'm going to assume that nothing is actually different. So I'm going to assume that the students come from the same population, from the population whose mean is 72, right? So I'm going to assume that the students come from the population whose mean is 72, so that means they're not any different from other students that took this exam. And what you're going to have to do, or what this teacher is going to have to do, is to prove me wrong. Okay? That's the idea. So in hypothesis testing, we're always assuming that nothing happens unless you give me enough evidence to contradict me. Okay, so that means innocent until proven guilty. Okay, so nothing's happening unless you prove that something did happen. So in last class, we know that if this is the case, then the distribution for the sample mean, so I know that the mean for this class, the distribution for the sample means, would have followed a distribution that is centered at 72, and that would have had a standard deviation of 12 over square root of n, which in this case is 30. Okay? Does this make sense for everybody? Can I see your show of hands for those of you who understand the idea of this? You don't necessarily have to remember the formulas, it's just the idea, the general idea of this. Okay. All right. So that means that for most samples of size 30, the mean is going to be around 72, right? So that means these are the values that are going to be the most likely, right? If I take a value, if I take a sample of size 30 from this population, then that means that most of my sample should be around 72, which means most of the average that I'll find will be like 71.5 or 72.5 or 72.3 and so on and so forth, right? But then there's also the chances, and some of you were in this situation last week, where I just happened to have one sample that was a little bit just full of people that were too good, or a sample that was a little bit full of people that were too bad, too weak. Okay, so that means that these values are going to be unlikely, right? But they still happen just by random chance. But then if I go even further away, then there's some values that are going to be really unlikely. Right? And so if I have a value for an average that is in the region that is very unlikely for me to observe, then it might just be that it wasn't caused just by chance. It was so unlikely that I obtained that value just by chance that there might be something in the works. Does everybody understand that? If so, please raise your hand. All right, so again, the idea is if we observe a value that is very unlikely, then it's then probably chance is not the only force at hand, right? So then it's possible that it wasn't caused by chance alone. Okay. Now there's the little problem over here of defining what very unlikely is, right? And for us, very unlikely is going to be the 5%. If it's less likely than 5% of the time, you can say that it's very unlikely and so that there's something else in the works. Okay, so we're going to go to the next page. And
Miss, can you go back for a second?
Yeah, okay. And so we're going to define what it means to be very unlikely. So I know that most likely means around the middle, and so very unlikely, like the further away I am from the center, the more unlikely it is for me to observe those values, right? Something like that, right? So it's more unlikely the more I get to the right of the distribution. Does everyone understand this? Please raise your hand if you do. Okay, so I'm going to go to the next section. If afterward you need more time to copy, you can ask me to go back. But I'll try to define what I mean by very unlikely in this case. Again, I keep repeating the same words, but I'm hoping that this will make it a little bit easier. So what I said is, okay, if my value is very unlikely, then I will conclude that that it was the method, the teaching method that actually made a difference. Well, this is supposed to be like nice, but of course. And so to define what I mean by likely or unlikely, I said, I'm going to say that it's okay as long as it was in the top 5%. So I'm going to define extreme or unlikely as 5%, the top 5%. And the rest is going to be assumed to be more or less usual, okay? So this is what I'm going to call usual. Whereas this over here, so this is the region that I consider to be usual. Whereas this is the region that I say, oh, this only happens about 5% of the time, so this is pretty rare, okay? Or pretty extreme. Does that make sense for everybody? If so, please raise your hand. Okay. All right, so there's two ways that we can do this problem. I'm only going to explain one, which is the one that we're going to use in the class. And so, yeah. So the idea over here is I'm going to find a boundary that separates what's rare from what's usual, okay? Because I'm going to find this boundary between what's rare and what's usual, I can then compute the value for my sample, and I can see whether it corresponds to the region that is rare or to the region that is usual, okay? So I know that over here, my sample average followed a normal distribution with parameters. Okay, you don't have to copy this, just an idea. 72 and standard deviation 12 over square root of 30. But because I always want to come back to the normal distribution with mean 0 and standard deviation 1, I'm going to have the following. X bar minus 72 divided by 12 over square root of 30. This is going to follow a normal distribution with parameters 0 and 1, okay? And there's really no mystery to this. All that you're doing is subtracting the average so that you set the mean to be equal to 0, and you're dividing by the standard deviation so that we get a standard deviation equal to 1, remember? So this is just by computing Z. This is something we did before, but basically the idea is just to get to a standard normal distribution so that then here I can just consider this to be a standard normal distribution.
Sorry, maybe I missed it, but where did 12 and square root of 30 come from?
I just specified that here.
Oh, okay. I'm sorry, I didn't see that.
Yeah. So this was just given. This is information that you would be given in any case like this.
Yeah.
Yeah. Okay. And because of this, I know that the value that is going to separate this, the top 5% from the bottom 95%, if I were to look at my Z table, don't rush it. We are going to do examples for this. It's just an idea. It's just the explanation for why this works. the boundary that separates top 5% from bottom 95% would be 1.645. Right? So this is what separates the top 5% from the bottom 95%. Okay? So if I got a result that is larger than 1.645, then I'm in the rare situation, and so that means that my result cannot just be explained by chance. But if I am on the usual side, so if I have a value that is smaller than 1.645, then my result was to be expected, and so I can conclude that actually this was just a matter of random chance. The 75 was just because of natural variation that there is in choosing one sample. Can I please see a show of hands for those of you who understand the reasoning behind this?
Miss, could you show the calculations again?
Yes, so over here I'm just saying because the normal distribution has a mean of 72, a standard deviation of 12 over square root of 30, if I subtract the mean and divide by the standard deviation, that will have a normal distribution with mean 0 and 1, so a standard normal distribution. That's just for me to be able to go back to my standard distribution table.
But do you want us to write it down?
You don't have to write it down. You'll have all of the information later. This is just like ideas.
Okay.
All right, and so that means if a result is rare or extreme, then it is unlikely that it came from this population. And there might be another reason why our result was rare. Likely that it came from this population. So what we're going to do is to find the value for our result. So find our x bar minus 72 divided by 12 over square root of 30. That was a lot of words to make it sound simple, but it's really not that bad. And we're going to see whether it falls in a rare region or in our normal region. Okay. So here I go. I'm going to have x bar minus 72 divided by s, which is 12 over square root of 30. This should be, this is going to have this type of distribution. Now, what I want to see is, once I plug in the value that I actually found for my average, is this going to be in the usual region or in the rare region? Okay, so that means this is going to be equal to approximately, no, not approximately, I can replace x bar with 75, so this is 75 minus 72 divided by 12 over square root of 30. Again, I'm just looking at the value that I found for my sample, and this is approximately 1.37. Okay, so I found the result 1.37, and what that means is, from samples of size 30, I expected means to be distributed approximately like this. From my particular sample, I found a result of 1.37. So 1.37 standard deviations above what I would have expected normally, which is here. Now, that is not that extreme. It is not that good. It is not even in the top 5% of the results that I would have expected. And so that means that getting a 75% from a population whose mean was 72 and standard deviation was 12, and from a sample of 30 people, is pretty likely because because it's fairly close to the mean, right? So I have that this population had such a large variation that I should have expected quite a bit of variation between the averages themselves. And so here I find that having 75 is actually not that extreme a result. Does that make sense for everyone? Yeah, so this is not that extreme a result, which means that I can't conclude that there's an actual difference, right? So this means that I'm not in the top 5% of the distribution. And so that means that my result was actually could be explained by chance alone, right? So I could have said, oh, actually, this result, the 75, the reason that I got such a high result actually could just be because I happened to have students in the class that were a little bit strong. Does this make sense for everybody? Can I see a show of hands for those of you who understand the logic behind this? The logic is the most difficult part in this section. Once you get the logic, the rest is just like an algorithm. You just check things. Okay, another thing that we could say is, I know that my result over here, so I know that I'm not in the top 5%. Actually, my result was in this region, which was the usual region, which means that getting a result as large as this one, or even a little bit larger, was more likely than 5%. Right? So my result was more likely than 5%, which is why I can't assume that it is that extreme. It's actually fairly common, and so I can't conclude that this is due just to chance. Does everyone understand that? Okay, so I'm going to write the logic steps, and then we're going to have one of the examples. I think today we're only going to be able to cover one of the examples. And I think that's it. Then on Tuesday, I'll cover another 2 types of tests, and we'll do practice, and you'll have an assignment by Thursday, just 3 problems. I'll post it right away, but you won't have the material finished until Tuesday, but you'll have the time to practice a little bit on Tuesday as well, okay? Is this all right for everybody?
Yes.
Okay, good. Okay, so everyone please lower your hands. So the idea that I want to, what I want you to remember over here is that this is always under the idea that we are going to be innocent until proven guilty. Right? So if you want to show some kind of significance, of statistical significance, you're going to have to show, like, to provide information in order to prove what you're trying to show. It's not enough to just say, oh, this is the truth and you have to disprove it. No, you, from whatever evidence that you want, if you want to actually show something, you're gonna have to show that that is the case. So in this case, and here we're going to introduce some vocabulary. So I'm going to start with the following. We start by assuming that there is nothing there. What do I mean by nothing there? I mean, we're going to assume that there's no noteworthy reason why something is happening, right? So in this case, for example, what we assumed is that there is no effect of the teaching method in the grades, right? So that means we are assuming that this comes from the same population that has an average of 72. We assume that there is nothing there. If you think there is something there, you will have to prove it by showing evidence. Okay, so evidence is going to be the key over here. You're going to have to show enough information to prove that there is something there. Okay, so this teacher had to have enough evidence to say my method is what's making them better. Once you have assumed that there's nothing there, we're going to have to determine how sure we want to be, like how much evidence do you want to have before you make a decision, right? So you are going to determine something that is called a level of significance. So we set a level of significance, or significance level, which is called alpha. You can just write the little almost fish thingy on the Greek A, so alpha. That determines how much evidence you want. That determines how much evidence you want before making a decision, right? So a small level of significance means we will require stronger evidence to show that there is something there, okay? So if you have a large level of significance, you need some evidence, but if you have a small level of significance, that means you want to be more precise, which means that you're going to need more evidence, stronger evidence, a more decisive result, a more extreme result in order to conclude that there is something there, okay? So higher level of significance means you can have some evidence and that might be enough, but if you want a small level of significance, like if you set your level of significance smaller, then that means that you will have to show more evidence, stronger evidence, more convincing evidence before you conclude that there is something. For 3, we're going to determine how likely our result is. I'm going to set a reminder. So remember, we assumed that there was nothing there. Okay. So to determine how likely our result is, we're going to use something that is called the critical value. This is called the critical value, which is the boundary that separates the usual results from the extreme results. Okay, and here's how we reach a conclusion. If my value, so if our sample produces a value that is in the extreme region, then we conclude that there is probably something there. There is probably something there. We say that we reject the idea that there's nothing there. So that means we're contradicting that there's nothing there. Questions, comments? Okay, so in our case, text. For the first section, what we need to do is to determine what nothing there and something there means. Okay, so in this case, we call those hypotheses. So we're going to talk about H0, which is it's called the null hypothesis. Null hypothesis, which is the idea that there's nothing there. Okay, and for the example that we covered just now, that was that mu, I don't have the symbols, let me just, there you go. There you go. So this was that mu, nothing there, meant mu is equal to 72. Okay. Then we have the alternative hypothesis, so what we're trying to prove. Which is what we're trying to prove, alternative hypothesis, which means the something there. And in this case, that was that mu was larger than 72. This is what he was trying to prove, right? That the mean was actually larger than 72, so larger than for the rest of the students. If you understand this so far, please raise your hand.
No, miss.
Okay, so the null hypothesis is a thing that we assume means nothing's there. So that's what we're going to start by assuming. So that means we have that H null hypothesis means, okay, we assume that there's actually no difference between the students in this teacher's class and the students in any other class. Right? So that means that the mean for these students is the same as the mean for the rest of the students, which is 70. That means there's nothing there, there's no mystery. The alternative hypothesis is what we're trying to prove, what this teacher was trying to prove, which is that there was actually something there, which means that mu had to be larger than 72. Right? So that means his average actually was, so the average for his class was actually larger than 72. Okay, so that means that there was a significant difference. Does that make sense?
Yeah, a bit more.
Okay. Then we set a level of significance, which was the thing that we said, okay, actually, if you're in the top 5%, I'll believe you. So in this case, we set alpha to be equal to 5%. Right? And so that meant that for us to conclude that there was something there, our sample will have to be in the 5% or the alpha percent, depending on what the value is. This could be 1%, 10%, whatever it is, in the 5% most unusual values. And then for the third part, we said, actually, I know that the boundary that separates the top 5% from the rest was 1.645. I found the value for hours, and it wasn't larger than 1.645, so I can't conclude that there's anything there. Right? So what we did is we said, find the boundary that separates the usual results from the extreme results. So we found our critical value was 1.645. Right? So this separated top 5% from bottom 95%. Then we found our sample value, which is called the test statistic, which means the statistic that we're going to use in order to perform the test, was 1.37. And that means that this was not more extreme, not in the extreme values. And so we concluded that there was nothing there, that this result could have very well been explained just by chance, and so that we have no, we don't have enough evidence to conclude that there was actually something there. Does this make sense for everybody? Can I see a show of hands for those of you who get more or less the idea of this? Please keep it raised once you raise your hand. I have about half the class with their hands up. Is there anybody that does not understand and that is not saying something? Please write either on the chat or on the... Okay, so I'll do an example. Hopefully I'll have the time to do at least 1 or 2 examples. But to do that, I'm going to formulate the actual test. So this is kind of the idea. Whenever you are trying to understand what we're doing, I think this is what you should go back to. Okay, so this is really formulating what the idea is, what each piece corresponds to. So it's like kind of the logic versus what we're actually doing. Then I'm going to write a bunch of lists of things, but what you need to remember is really just this, okay? We're only going to do 3 types of tests. We're going to cover 1 of them today. I'll post problems for this probably, I would say tomorrow. Don't trust me to post them today. I'll try, but if not, then definitely tomorrow.
Oh, sorry.
Yeah.
Can you just go back to the questions really, like the steps really quickly?
This?
Yeah, thank you.
Okay. So I'll post a couple of problems today, and then we'll finish the other types of problems on Tuesday, but it will be a lot easier for me to explain if you have tried the problems that follow what we do today. Okay, so in the next example, I'm going to write an actual test. Okay, so the first test that we're going to see today is called the one sample.
Miss, what do you mean by test?
How do I explain it? What we're trying to do is we're trying to test hypotheses, right? We're trying to say, is this hypothesis a valid explanation? Yes or no? How sure am I? So I'm trying to test whether a hypothesis is a valid explanation and then to give a level of confidence of how much I think that is a valid explanation or not, right? So what I'm trying to do is just test those hypotheses. These are all called hypothesis tests, but essentially what we're trying to do is prove a statement or disprove another statement.
Thank you.
So for the one sample t-test, which is the one that we've been talking about, or the one that's the most similar to the one that we've been talking about, we're going to have the following assumptions. Assumptions, which are that. First thing, and this is gonna sound really similar, which is that the original distribution is approximately normal. And the second thing that we're going to assume is that there's no outliers. So we only will be able to use this test if our original distribution is approximately normal and there are no outliers. Okay, this is not something that you're going to have to worry for the problems that I give in class. But once we're doing the research project, if you ever have a doubt about whether you can use a given test, you should definitely come see me and talk to me about it, about whether it's a reasonable option to use that test. So assumptions is that, and the null hypothesis in this case. For this test, what we're going to try to show is that a mean is either significantly larger than a given value, significantly smaller than a given value, or significantly different than a given value. To do that, we're going to have to start with something to disprove. That thing that we're disproving, remember, is called the null hypothesis. So the null hypothesis is the thing that we're trying to disprove. And in this case, our null hypothesis is going to be, it's always denoted by H naught or H0. And that is that mu is equal to the value that you're comparing it to. Okay, so if I'm trying to show that a mean is larger than 4, then I'm going to start with the hypothesis that the mean is actually equal to 4. If I'm trying to show that a mean is smaller than, I don't know, 7,000, then I'm going to start with a null hypothesis that the mean is actually equal to 7,000, right? Because this is what we're trying to disprove. So my null hypothesis is going to be this. And then depending on the alternative hypothesis, my test is going to change a little bit. But before I get to that, I'm going to talk about the test statistic. And this is the number that I will compute from my sample, right? So this is going to be very similar to what we had in the previous example. So the test statistic means from the sample. It's a number that I'm computing from my sample. And here this test statistic is called T. And it's going to be the mean for my sample minus the value that I'm comparing this to, so mu naught. This is mu naught, mu with a little 0. Okay, so mu 0. Okay. So the test statistic is going to be x bar minus mu naught, which is the value that I'm comparing this to, divided by the sample standard deviation, the whole thing over square root of the sample size. Okay, so this is just, if we go back to what we have, these are just the assumptions. That means when can I use this test? The null hypothesis is just saying, this is what I'm trying to disprove. I'm trying to show that the mean is not equal to mu 0, some value. Mu 0 is just a label for some value. It could be 7, 2, minus 1, whatever it is, okay? Just some value. The test statistic is the value that I'm going to compute from my sample. And then I'm going to list the conditions that I'm going to have to satisfy if I want to prove or disprove something. Okay, so there's different possible alternative hypotheses. Just so remember. Then here I'll have alternative hypothesis. And depending on what the alternative hypothesis is, I will reject under different conditions. So I have, if what I'm trying to prove, the alternative hypothesis, what I'm trying to prove is that my mean is larger than the value that I'm comparing it to, then I will reject the null hypothesis. I will say, actually, this could not have been an explanation for the value that I found. I will reject if I'm in the top something percent. How much percent? Well, it always depends on the percentage that you've chosen originally, which of course you will always be given. Does everybody understand this? Yeah, so I'll reject if I'm in an extreme case where it's very large. So if I'm trying to disprove that mu is equal to mu naught, if I'm trying to show, to demonstrate that my mean is larger than some value, then I'm going to reject my null hypothesis if my mean is very large. Okay, how large? Larger than t alpha n minus 1. I'll write it down, but I'll write it down again here. So
Miss.
Yep.
What's the HA?
Alternative hypothesis. So this is option number 1, and we're gonna have 3 cases. So we're going to reject the null hypothesis. So our assumption, our original assumption as a possible explanation, if my test statistic, which is this one over here, remember this one, my test statistic is larger than t alpha n minus 1. So that's the first possible alternative hypothesis that I have. The second possible alternative hypothesis that I have is that mu is smaller than the comparison value. In which case, I'm trying to show that the mean for my population is actually smaller than a given value. So that means that I will reject if I have an extremely, not large, but an extremely small value, right? So if I have a value that is a lot below the value that I'm comparing it to, then I'm going to conclude that the value of the mean cannot possibly have been the same as the original value that I said, right? So if I have something like this, I'm going to reject my null hypothesis. I'm going to say this cannot be caused by chance. This has to have been caused by something else. So that's if my value is smaller than minus t alpha n minus 1. Because if you remember, this is like symmetric and everything. So reject. So we say h naught, the idea that the mean was actually equal, cannot be a possible explanation for this extreme result if the result for my sample, t over here, the sample statistic, is smaller than minus t alpha n minus 1. Okay, so this is option number 2. Now, these are completely distinct cases. In the first possible alternative hypothesis, you're showing that something is larger. In the second case, you're showing that something is smaller. That means these are different types of examples, okay? And depending on the type of example that you're using, you're going to use one or the other of the tests. Finally, the last possibility is that you're not showing that the mean is larger or smaller than a given value. You're just showing that the mean is different than a given value. So maybe, for example, you're not trying to show that pulling an all-nighter makes you better at tests. You're just showing that pulling an all-nighter makes you have a different grade that you would have normally had on a given test, in which case you're going to reject if the value is either too large or too small. Right? So if your value is too large, then that means it's very different from the value that you expected. If it's very small, then it's going to be very different from the value that you expected. Of course, in this case, you also want to only reject the extreme alpha percent, which means that you're going to reject if you're above T alpha over 2 because you're only going to chop alpha over 2 from both sides. And minus 1. And n minus 1.
Miss?
Yep.
What's the like apostrophe? Or like the virgule beside the minus T.
Minus T alpha n minus 1.
Yeah, but like what's like, oh, it's just separating them?
Yes,
Like
it's just like
okay.
it's exactly the same writing. It's just
yeah, I know.
Yeah. The pen sometimes is not recognized as lifting from the tablet. So
I thought it did something to.
No, there's no magic.
Okay.
So then we're going to reject H naught. So we're going to say chance is not a reasonable explanation if T is larger than T alpha over 2. So if it's in the top alpha over 2%, or T is smaller than minus T alpha over 2 and minus 1. Okay, so I'm going to do a problem on the board. I don't want you to spend too much time writing it. The video is going to be posted tonight. I'll make sure to post it tonight so that you can take notes if you can. But what I want you to do is to follow what I'm trying to do. And I'm going to post this video along with another video that also shows how to do another example of the same type online. Okay, so the idea is really for you to get an idea of how to do this. And because I'll pose the practice problems, you can try 2 practice problems before next class so that you can ask me your questions then. Please raise your hand if you understand what I just said, and if it's okay. Okay, so it's just, getting some practice. If you don't have the time, then you don't have the time and it's okay. But if you do, then it would really help you in understanding and me in understanding where you are. So what I'm going to solve is the following example. Yeah, there you go. Oops. So we have that a moving company has claimed that the average weight of a fully loaded moving van is 12,000 pounds. The highway patrol the highway patrol decides to check this claim, and a random sample of 42 moving vans shows that the sample average weight is 12,250 pounds with a sample standard deviation of 830 pounds. The weight come from an approximately normal distribution, and this indicates that the average weight of a moving van is different than 12,000 pounds. That's what we're going to try to test. We're going to use a level of significance of 1%. Okay, a lot of information. I'm going to start by trying to identify each of the pieces that I need, right? So the first thing is that a moving company claims that the average weight of a fully loaded van is 12,000 pounds. So that number is probably going to be important. Then I have that a random sample of 42 moving vans, so 42 moving vans. That means that this is probably the sample from which I collected the data. Then the sample average weight is 12,250 pounds. And a sample standard deviation was 830 pounds. Then you can have blah, blah, blah. Does this indicate that the average weight of a moving van is different from 12,000 pounds? Use a level of significance of 1%. Okay, so I really want to gather all my information before I start solving the problem. All right, so first thing is I have 42 moving vans. I have that this is n is equal to 42. Now, I don't want to start with the 12,000 pounds over here because I don't know if that's the value that I'm supposed to be comparing to, if this is the mean for my population, if this is the mean for my sample. I don't know exactly what I'm dealing with here. So I want to start with the things that are really clear from the problem. Okay. Then, from 42 moving vans, I got a sample average weight of, so sample average weight, I know that that's denoted by X bar. Okay. Sample average weight of 12,250 pounds. Then I have a sample standard deviation of 830. Sample standard deviation, I know that that's given by S. Right? And this is 830. And then I was asked to evaluate level of significance of 1%. If you understand everything that I've written so far, please raise your hand. Okay. All right, okay, that's good enough. All right, so the 12,000 pounds over here is not really any of the pieces of information that I got from my sample. Instead, what I'm going to try to do is to show or to determine whether the weight of a moving van is different from 12,000 pounds, right? So that means that that's probably going to be the value that I'm going to be comparing everything to, right? So what I'm trying to determine, what I'm trying to prove is that mu is different. So the mean average weight of a moving van is different than 12,000 pounds. Okay, do I have any questions about this? No questions, okay. So this is what we're trying to prove. And so I'm going to use the same steps every single time that I'm doing a problem with hypothesis testing. The first thing that we're going to do every single time is, and I'm going to write this list in the video that I'm going to post with the second example. So I'll post a list of the steps that you need to follow so that it's a little bit more clear when you're trying problems on your own. So first thing is to set the hypotheses. So that means H naught, which is my null hypothesis, is the probability, is the hypothesis where nothing's going on, right? So actually nothing's going on. That means in this case, we're going to say, actually, yes, this is equal to 12,000 pounds. So the mean weight for the moving, so like mu is equal to the mean weight for moving vans and so the null hypothesis is going to be there's nothing there. There's is actually true. Mu is equal to 12,000. The alternative hypothesis is the thing that we're trying to show. So in this case, we're trying to show that mu is going to be different than 12,000 pounds. And this is always something that comes from the statement. So here you're being asked to show that it is different. Okay, so that's why we choose different over here. In the second piece over here, we're just going to take the time to recognize that the level of significance is 1%, so that we remember that this is the value that we need to look for. Okay, so this is always a step that you should use. And then in step 3, which is to actually perform the test, so this also corresponds to what we did in this section, right? So first, let's look at the assumptions. Second, let's set the level of significance. And third, let's actually perform the test. Right? So third, let's actually perform the test. That means first, we need to recognize what test we're using. In this case, we only have one. So that means that's the one that we're going to have to use. One sample t-test. The second thing that we're going to do is to find the critical value. Okay. Now, in this case, we have to show that this is different than 12,000, which means that we're going to have a two-tailed test. because we're trying to show that this is different, not necessarily larger or smaller, but both. So we're going to have what we call a two-tailed test, okay? Now, because this is the case that I'm considering, I'm going to go to this case. And what I'm going to do is a two-tailed test with a level of significance that I knew to be 0.01. Oops. Okay. All right. So here I'm going to have 0.01, and then that's why I have an expression over here that says two-tailed. 0.01. And my sample was of size 40. Size 42, sorry, which means that we would have to look at the line that is 41. In this case, I don't have a line that's 41, and so the closest value that I have is 2.704. This is the part that's the trickiest. Does everybody understand this?
Not really.
Okay, so I'm doing a test. I'm trying to chop both sides, right? So I'm trying to determine whether my value is too large or too small to be deemed equal to 12,000. And so I'm looking at a two-tailed test because I will say that my value is too different from 12,000 if either the average for the sample is very large or if it's very small. So that means I'm going to look at a two-tailed test, okay?
Okay, yeah.
And then I know that my level of significance has to be 1%, so 0.01, and my sample size is the closest to 40. If you can find the exact value in the rows, it's perfect, but here 41 is not in my table, so I'll have to go to 40.
Are you looking where? Oh, 40 is on the left.
Yeah.
Okay, yeah.
Okay. So I get 2.704. That's the value over here. Where am I? You sure? There you go. So that means that this is 2.704. But it was a two-tailed test, so I'll also reject if this is minus 2.704. So if I have a value that is either larger than 2.704 or smaller than minus 2.704, then I'll reject my hypothesis. Does everybody understand this? Okay. So then I'll compute my test statistic, which is the value for my sample. Right, so I already said the values over here. So this is essentially the thing that's separating the middle 99% from the extreme 1%. So what I'm saying here is if my result for my sample was in the extreme 1%, then I'll say actually it was too rare. So my test statistic here is just T, which is given by this formula over here. And so that's sample average minus comparison value divided by standard deviation over N. So sample average is 12,250 minus comparison value, which is 12,000, divided by standard deviation, which is 830, over square root of N, which is square root of 42. And here, this is going to be equal to approximately 1.95. If I look at my graph, we're almost done. I'll have 2 minutes. I know it's going to be 1 minute late, but then you'll be done with it and you'll be able to solve one of the problems. So you have that 1.95 is not larger than 2.704, nor smaller than negative 2.704. It's probably somewhere around here, which means that it's in the most usual 99%. And you don't have enough evidence to say that this mean, like the mean for the weight of the moving bands, is actually different from 12,000. Okay, so I'll just write that little blob over here concluding, and then you're free to go. So what we say is that we can't reject H naught, which means we can't say that that was not a reasonable assumption. We say there is not enough evidence to conclude that the mean weight of the moving bands is different than 12,000. right? Why is there no evidence? Well, because the value that we found for our sample was in the most common 99%. So that means that 99%, like, yeah, I'm not in the most extreme 1% of the cases, and because that's the level of significance that I wanted to conclude this with, I couldn't show that this was actually not that this was different enough for me to conclude that it was different, right? So for me to say actually the weight is different, I have to show a lot of evidence. The difference has to be really stark. Now the difference over here wasn't large enough, and so I can't conclude that there's a significant difference. Is this okay for everyone? All right, so I'll post, as I said,